Okay, so at the start of this video for section 2.5, I wanted to put myself on camera here, make sure you remember I'm still here, just to reinforce that, there is an instructor behind this who does, care. Please, get in touch with me if you're having trouble. Come by office hours, contact me by email, whatever means makes sense, and I am happy to get with you. So we're going to be looking at section 2.5 today, talking about matrix factorization. Okay, so we're going to dive right into that here. Okay, so we're looking about a matrix factorization. So we know factorizations. That's a word we're familiar with. Okay, for example, if I have a number, let's say 16, I could write that as 2 times 8. So 2 and 8 is a factorization of 16. There certainly are others, right? We could do 1 and 16. We could also do 4 and 4. There's several factorizations, okay? So similarly, for a matrix A, there's going to be ways to factor this into 2 separate matrices, which I'm going to call A1 and A2, okay, just for the time being. Now, there are a few different methods for factorization. Okay? The 2 most common methods for factorization are LU factorization, which is actually what we're going to spend most of the time in this chapter, and QR factorization. Okay, and we will talk about QR factorization much later in the semester when we get to chapters 5 and 6. So QR factorization does come up, and there's also another factorization which is called diagonalization. A diagonalization is another factorization that comes up. Okay, those are our 3, and we will talk about QR and diagonalization. I will touch a little bit on diagonalization today in this video, but diagonalization is really a much later section in chapters 5 and 6. We talk a lot about those there. But we're going to talk about LU. And so L and U here are chosen because they stand for lower and upper. Okay, that's why it's called LU factorization. And the reason we want to do an LU factorization is we know that triangular matrices are very easy to work with. Okay, row operations can sometimes be very computationally difficult. We get fractions involved. We have a lot of tricky things that we have to deal with. But perhaps I could have 2 matrices here that were triangular. And I know that triangular matrices, if they're square, a triangular matrix may in fact be invertible. So maybe I have an A that's not invertible and I can turn it into 2 things that are, and I can do operations on those invertible matrices. Maybe A isn't even square, but one of these matrices that are my L and my U are square, which makes it invertible. And then I can do operations there. I can use those properties of invertibility to find out some additional information. Okay, so that's the important motivation for why we look at factorization. We want to get something that's easier for us to deal with. It's computationally more efficient, that we can work with at a much higher pace, so to speak. Okay, so we're looking at LU factorization. That's our driving force here. Okay, and so as with a great many times, we're usually looking at solving a matrix equation, right? I have a matrix X and a vector B. Maybe I have a series of things I'm interested in here for a vector B. Maybe I have AX equals a B2, and I have AX equals, again, vector X, vector B, B3. I don't know how many points I have for these, but I know that doing the row operations every time is very computationally difficult, okay? It's hard to train a computer to, harder, I shouldn't say hard. It's hard to train a computer on exactly what the right row operation steps are gonna be each time, what that process is. But if I can take 2 easier to deal with matrices, L and U, I can use those then in that same computation. So we're looking at factorizing this, or factoring this LU factorization to where I have a matrix L that is lower triangular and thus invertible, and then a matrix U that is upper triangular, but I can't guarantee it's invertible. Now, if, in fact, most of the time it very likely won't be, especially, U may not even be square, right? There's no reason to guarantee that U is square if the matrix A isn't square. Now, if the matrix A is square, then U will be square, but we're not guaranteed that it is invertible. In fact, if A is not invertible, we know that the product of 2 invertible matrices is invertible, okay? So we're looking for this L and U such that my matrix A is equal to L times U. Such that, I forgot that, there we go. Such that A is equal to L times U. Okay, that's what we're interested in. Okay, this L is invertible, so if A is invertible, a product of matrices are each invertible. So if A is invertible, U is invertible. If A is not invertible, U is not invertible, because if they were both invertible, then the product of two invertible matrices would be invertible. Okay, so we can at least get this factor where one of the matrices in the factoring is an invertible matrix. Okay, all right, so we said we're looking at solving this equation, AX equals B. Okay, we said that was the equation we're looking at solving, but I'm looking at when A is equal to LU. So I can take this and replace LU for A. Okay, then we also know that matrix algebra is associative. So I can do L times UX is equal to B. Okay, and UX, we're going to just name Y. Okay, so I'm going to let UX equal a unknown vector Y. Again, these are vectors when they're not matrices. X is a vector, B is a vector, okay, Y here is a vector. Okay, my matrices are L and U and A for that matter. Okay, so then once I let UX equal Y, now I have L times Y is equal to B. Okay, so now if I look in here, I have two equations. Okay, I have UX equals Y and LY equals B. Okay, so those are our two key equations here, because I can use these then to solve linear systems, just like I used linear systems before to solve various things. Okay, so let's look at an example of what we can solve. Okay, I'm going to keep those two equations visible here as they're important. So I'm going to have a matrix A. My matrix A is going to be a 3 by 3 matrix, 3, -6, 3 along the top row, -9, 15, -4 in the middle row, and then the bottom row 6, -9, and 2. Okay, and I'm going to give you, / the book may give you, the LU factorization. So 1, 0, 0 on the top row, -3, 1, 0 on the middle row, 2, -1, 1 on the bottom row. Okay, that is my matrix L. Okay, notice it is lower triangular. Okay, because I have these entries on the diagonal. Everything above the diagonal is 0. Now I'm going to have my matrix A. Since I have 3 by 3 here and 3 by 3 here, my matrix U is also going to be square. It's going to be 3, -6, 3, 0, -3, 5, and then 0, 0, 1. Okay, so there's my matrix U. So I've given you the LU factorization here. Okay, and what we're interested in figuring out is solve AX equals B when B is equal to the following vector, 6, 2, -1. Okay, so again, I have my two equations here, UX equals Y and LY equals B. Okay, so I know B, I don't know Y yet, so I need to start here. Okay, so LY equals B. Okay, so we're doing LY is equal to B. We're going to solve that using what we know about linear systems. Okay, so given what we know about linear systems, I have my matrix L, 1, 0, 0, 3, -3, 1, 0, 2, -1, 1. Okay, we would set this equal to x1, x2, x3. Then we would set it equal to my vector B, 6, 2, -1. Okay, you could augment. You can also take the inverse. Okay, inverse may be difficult. Augmenting is probably easier here because I have a fairly easy triangular matrix to accommodate. Okay, that's why we like triangular matrices. -3, 1, 0, 2, -1, 1. I'm going to augment that with 6, 2, -1. Okay, and we're going to start doing some row operations on this. Okay, so I need 3 copies of row 1 plus row 2 is going to replace row 2 because I'm getting zeros below. Okay, I'm also going to do negative 2 copies of row 1 plus row 3 is going to replace row 3. Okay, so let's do those row operations here. First row is going to be unchanged, 1, 0, 0, 6. 1 and 0, I'm sorry, negative 3 and 3 is going to make 0. Notice this is a positive 3 here. Positive 3. 0 and 1 is 0. 0 and 0 is 0. Okay, I multiplied 6 by 3. Multiplied 6 by 3 and I got 18. 18 plus 2 is going to be 20. Okay, 3 times 6 plus the 2 here. Okay, going down to the next row now, I'm multiplying by negative 2, I said. So negative 2, 1 and 0, 1 and 2 and negative 2 is going to be 0. 0 and negative 1 is going to be negative 1. And then the last row, I've got 0 and 1, and the last column makes 1. Okay, negative 2 times a negative 6 is a negative 12. Add the negative 1 to that, I get a negative 13. Okay, now I need one more. So I've got my pivot. I've got zeros below. I've got a pivot here. I need a 0 below it. So I'm going to do row 2 plus row 3 replaces row 3. Okay, so I've got 1, 0, 0, 6 along the top here. 0, 1, 0, 20 in the middle row. Bottom row now, 0 and 0 is going to be 0. 1 and negative 1 is 0. 0 and 1 is 1. 20 and negative 13 add up to make 7. Okay, so I got off the picture there. But you see we got 1 and negative 1 makes 0. 0, 1 makes 0. I've got my nice identity here. So I have my y vector now is 6, 20, and 7. Okay, so y is 6, 20, and 7. Let's go to a new page here. Okay, remember that I'm using LU factorization. Ux is equal to b. Sorry, ux equal to y. Kind of ahead of myself. Ux is equal to y, and I already did ly is equal to b. We found that y was equal to 6, 20, and 7. So now I'm doing ux. So remember what your U matrix was. And make it visible here for us. There's our U, 3, negative 6, 3, 0, negative 3, 5, 0, 0, 1. Okay, so ux equals y. We're going to have 3, negative 6, 3, 0, negative 3, 5, 0, 0, and 1. I remember we're setting that equal to x1, x2, x3. I got ahead of myself again. I said set equal to. Now we're setting it equal to our y vector, 6, 20, and 7. Okay, so now I can set up an augmented matrix. 3, negative 6, 3, 6, 0, negative 3, 5, 20, 0, 0, 1, 7. Okay. So I've already got zeros below, so I need to work up. Work up. So I'm going to take row 3, but I need negative 5 copies of it. Add it to row 2 and replace row 2. because I'm getting the 1 and 5 together to make 0. And I'm going to need negative 3 copies of row 3. Add that to row 1 and replace row 1. Okay, so I get row equivalents here. My new row 1, 0 and 3 is 3. 0 and negative 6 is negative 6. Negative 3 and 3 is 0. Negative 3 times 7 is a negative 21. Plus 6 is a negative 15. Okay, my new middle row, 0 and 0 is 0. 0 and negative 3 is negative 3. Negative 5 and positive 5 is 0. Okay, negative 5 times 7 is a negative 35. Add that to 20 and I get negative 15. Negative 35 plus 20 is negative 15. Okay, a little coincidence there that those are both negative 15. Okay, third row is unchanged. Okay, one more here. I've got a pivot here. I need to get a 0 above it. So 2 copies of row 2. Add that to row, I need negative 2 copies because they're the same sign right now. Add that to row 1 and replace row 1. Okay, again, shifting over so we get the whole thing in the picture here. Okay, the new row 1, 0 and 3 is 3. Positive 6 and negative 6 makes 0. 0 and 0 makes 0. Okay, negative 2 here times negative 15 is a positive 30. 30 minus 15 is a positive 15. So 3, 0, 0, 15. Middle row is unchanged. Bottom row is unchanged. Okay, so I'm there except for scaling. I need to do row 2 divided by 3 and row 1 divided by 3. Okay, and so I should be able to see my vector here, my vector x. 15 divided by 3 is 5. Row 2 is getting divided by negative 3. Negative 15 divided by negative 3 is 5. And then this last coordinate is already 7, and it's already scaled. So my x vector is 5, 5, 7. Okay. Now, is that appreciably easier than doing row operations? Well, especially with a calculator, probably not, to be perfectly honest. Okay. But we will encounter matrices where it is better if you have a factored matrix. It's easier row operations to do. And as you build out your library of techniques, and if you go on to work in this in a programming context, it's important that you understand how the computer is doing things on the back end. The computers work through LU factorization. A couple of the questions we'll talk about what MATLAB does. We're not going to be using MATLAB, but we'll talk about how MATLAB does it and understand where the errors occur and what comes up as the difficulties. Okay. All right, so let's recap what we did, right? I have two equations, ux equals y and ly equals b, okay? So I know the vector b and I know the matrix L. I can take this equation, row reduce it, simplify it. That gets me my vector y. Plug your vector y in here for ux, and that produces your vector x, okay? So you're finding the vector x and the vector y using row operations. Okay. Now, the next thing we want to use for this is we want to, sorry, I'm getting ahead of myself. I have one more example for ly. We are eventually going to do our own LU factorization, but I want to do another example of this type so you get the idea of what's taking place. Okay, I'm going to use the calculator a little more on this example so that you know how that works. So I'm going to have a matrix A here. It's going to be a 4 by 4 matrix. So it's a pretty big matrix. 1, -2, -2, -3, my top row. Second row, 3, -9, 0, -9. Third row, -1, 2, 4, 7. And the bottom row, -3, -6, 26, and 2. Okay, and again, I'm going to give you the LU factorization. Or the book's going to give you the LU factorization. That's 1, 0, 0, 0. 3, 1, 0, 0. So this is the L factorization. Notice L comes before U in this factorization. Okay, the way to remember that is that they are in alphabetical order. L comes before U in the alphabet. So in your factorization, L should come before U. Okay, remember matrix multiplication is not commutative. So it is important that we preserve that order. Okay, so here's our matrix L. Notice it's lower triangular again. So 1, 0, 0, 0, 3, 1, 0, 0, -1, 0, 1, 0, -3, 4, -2, and 1. I'm going to multiply that now by a matrix, I should say, U. 1, -2, -2, -3. Now you should start picking up those first row of U tends to be very similar, if not identical, to your to your starting matrix, okay, in this factorization. So that makes things a little bit easier and gives you a little bit of a reasonability check later when you're setting up those L and U yourself, okay? Let me zoom out just a little bit so you get the whole picture of the equation here. Okay, there's my A, there's my L, there's my U, okay? I'm going to write up here in the corner our equations, ux equals y, and ly is equal to b. Okay, ux equals y, ly is equal to b. So I'm going to take u, I need my v vector. I haven't given you b yet. So b that I'm interested in is going to be 1, 6, 0, and 3. Okay, So first, I need to take B and find Y. Okay, so Ly equals B. So Ly equals B. I'm going to write L 1 0 0 0 3 1 0 0 negative 1 0 1 0 negative 3 4 negative 2 1. Augment that with my B vector 1 6 0 3. Okay, we're going to row reduce that. Remember that in the conditions, L was invertible. Okay, I know L is invertible because it's lower triangular. So I know that my resulting row reduction is going to give me the identity with an appropriate augment here, okay, depending on what my row operations are. So take out your calculator. I'm going to do a 4 by 5 matrix. Okay, trying to get everything out of the glare. So I've got 1 0 0 0. There we go, that's better. Okay, I get 1 in the last column. Second row, 3 1 0 0 6. Third row, negative 1 0 1 0 0. Negative 3 4 negative 2 1 3. Okay, we're going to quit. We're going to go to matrix, go over to math, RREF, B command there, RREF of my matrix A that I just made, and I get 1 3 1 negative 4. Okay, so 1 3 1 negative 4. So this is my vector y. Okay, so then when I go to do ux equals b, ux equals y, I'm going to take my matrix U, negative 1, 1, negative 2, negative 2, negative 3, 0, negative 3, 6, 0, 0, 0, 2, 4, 0, 0, 0, 1. Augment that with 1, 3, 1, negative 4. Vector I just found for y. We're going to row reduce that. Okay, so again, I go 4 by 5 here. Worry about my glare. We'll get one where I can see it all. There we go. That'll work. So 4 by 5, 1, negative 2, negative 2, negative 3, 0, negative 3. Oh, I didn't get the fifth column. Sorry, 1 in the fifth column there. And I've got 0, negative 3, 6, 0, and 3. Third row, 0, 0, 2, 4, and 1. 0, 0, 0, 1, and negative 4. Okay. Do RREF of A again. Again, you can do second enter to make that command come up easily. And we see I have 38, 16, 8.5, and negative 4. Okay, so this again gives me the identity. Augmented with my solution, 38, 16, 8.5, and negative 4. So this vector here is my unknown x. Okay. Again, what's easier, that's not really our goal here, is not necessarily just total ease for our computations. We want to have a whole set of tools that we can use to help inform our decision making going forward. Okay. All right, so next we're going to have an algorithm for finding L and U. Okay, to this point, I've just given you L and U, and we've done these operations using our two equations, ux equals y and ly equals b. But we need a method for finding L and U, okay? We need a method for finding L and U. We're going to explain what that method is going to be, okay? Now, it's a little bit tricky to explain right offhand, okay? I'm going to show you the algorithm as the book explains it here, and then you're going to talk through an example and you'll get the feel for it, hopefully, as we're going. So we're going to reduce A to an echelon form U. Okay, so we do row operations to find U. Okay, then we place the entries in L such that the same sequence of row operations reduces L to I. Okay, so we're finding U using row operations just like we've always done. Okay, always done, going back all the way to the distant memory of chapter 1. Then we're going to do our entries in L using the same sequence. Okay, now this turns out to be a pretty arduous task, right? I have to find L and work backwards. Okay, so it turns out there's some easier techniques we can apply as we go here. Okay, so we're going to show you what that looks like. Okay, all right, so we're going to start with a pretty simple 2 by 2 matrix. Okay, so I take my 2 by 2 matrix here, we call it A, because we aren't super original in our naming. It's going to be 6, 12, 4, 5. Okay, a nice, fairly simple matrix. Now, it's important that many times we like to go through and scale to get 1 here. When you're doing LU factorization, so you're trying to find the L and U, you do not want to scale your matrix. You do not want to scale your rows, because if you scale your rows, you're losing some information, and you're going to wind up having to multiply that scale factor back in to get the appropriate vectors for the columns. Okay, so I'm going to take my matrix A, I'm going to row reduce it. So I'm going to take -2 row 1, add it to row 2, and replace row 2. Right? I'm keeping this as my pivot. Remember, make your upper left your pivot to get a 0 below it. Okay, so A then is equivalent to row 1 stays the same, 6, 4. We're going to divide, we're going to multiply. I get 6 times -2 is -12. 12 and -12 is 0. -2 times 4 is a -8. -8 plus 5 is a -3. Okay? Now, I have a pivot in every row. This is U. It's upper triangular. Hence the why we represent it with U. Okay, so for 2 by 2, it just took me one row operation to get there. For a 3 by 3, it may take me a few more. 4 by 4, a few more than that. But once you have your upper triangular, you are good with U. Okay, U is done. Okay. Now, what we want to do is identify where we first found each pivot. Okay, so I'm going to circle that as we went through here. We identified our first pivot here. Okay, my second pivot, I did a row operation. I got 0 here, so now this is my second pivot. Okay, so to make L, I'm going to take those pivot columns. So I'm going to take this column, okay, 6, 12. Remember, L should be lower triangular, so it's going to have a 0 in that upper position. Okay, then I want to take my pivot and everything below it. Well, in this case, that's just the pivot. Okay, so I take my pivot and everything below it. Okay, so I have my candidate here. Now, what I do need to do for L is I need to scale this to have 1s along the diagonal. Okay, so your L matrix in your LU factorization will have all 1s down the diagonal. So I'm going to take row 1 here and divide it by 6 because 6 is in that pivot position. I'm going to take row 2 and I'm going to divide it by -3 because -3 is in that pivot position. I said row 2, that should be column 2. Okay, I'm dividing the columns here. Okay, so L is going to be 1, 2, because 6 divided by 6 is 1, 12 divided by 6 is 2, 0, -3 divided by 3 is a positive 1. Okay, so my matrix A, which remember was 6, 4, 12, 5, is equal to L, 1, 0, 2, 1 that we just found, times U that we found just before, 6, 4, 0, -3. Okay, nothing wrong with using, going through and making sure that you did it right. So go through here and multiply. 1 times 6 is 6. 0 times 0 is 0. 6 plus 0 makes 6. First row, first column. First row, second column. 1 times 4 is 4, plus 0 times -3. So 4 plus 0 is 4. First row, second column matches. Now, second row, first column. 2 times 6 is 12. 1 times 0 is 0. Okay, that's 12 again. Second row, second column. 2 times 4 is 8. 1 minus 3 times -3 is -3. And 8 minus 3 is 5. So my LU factorization checks out. Okay, So you find U first by doing row operations, okay? Step 1, row operations, no scaling, okay? No scaling, just replacement to find U. So remember, U is upper triangular. Step 2, identify pivot columns. Keep numbers below the pivots. Okay, so in our case, we identified this 612 as a pivot column. First time we had it as a pivot was here. I kept the numbers below it, 6 and 12. Second one, pivot column, I identified the -3. I kept the numbers below it, -3. I didn't keep the 4. We discarded the 4 and replaced it with zeros, okay? So I put zeros above the pivots. Okay, zeros above. Step 3, scale the columns by the pivot position. In our case, that was the 6 and the -3. So we scaled the 6 by 6, divided by 6. Scaled the -3 by -3, dividing by that. Scale the columns by the pivot positions, okay? And then you have L. And that produces L. So those are our steps, okay? All right, so let's bite off a 3 by 3 matrix here. Okay, so 3 by 3. So I'm going to have matrix A. My matrix A is going to be 2, 3, 2, 4, 13, 9, -6, 5, 4 on the bottom row. Okay, I'm going to start doing row operations. Remember, don't scale it, don't divide by 2 or anything. So I need -2 copies of row 1 plus row 2. Why? Because -2 times 2 will be -4, and 4 and 4, -4 and 4 will make 0. Same thing in the third row. So 3 copies of row 1 plus row 3 will replace row 3. All right? First row is unchanged. Remember, I said that the first row would be unchanged in U. Okay, so notice that first row is unchanged because we're only doing row operations below it. -4 and 4 makes 0. -2 times 3 is a -6. -6 plus 13 is 7. Okay, 3 times 2 here is 6. 6 plus 9 is 15. Sorry, -6. Try that again. Sorry, I got that crossed up there. -2 times, I'm looking at the third one. -2 times 2 is -4. 9 and -4 makes 5. That looks better. I knew something was amiss. Okay, -2 times 2 is -4. 9 minus 4 is 5. Okay. Third row now. 6 and -6 is going to be 0. Okay, 3 times 3 is 9. 9 plus 5 is 14. 3 times 2 is 6. 6 plus 4 is 10. Okay, so here was my first pivot. I'm going to go ahead and circle it so I remember where they were. Now I've identified my second pivot. So now we're going to go below that. So -2, row 2. Add that to row 3. That's going to replace row 3. And actually, that's going to kill off both numbers here in the third row. So I have 2, 3, 2 top row unchanged. 0, 7, 5 second row doesn't change. 0 and 0 makes 0. -14 and 14 makes 0. -10 and 10 makes 0. So there is my matrix U. Okay. Now notice I only had the 2 pivots here. Okay, just the 2 pivots. So I need to take those 2 pivots and slide them down. Okay, so I have my first pivot row here, 2, 4, -6. Okay, so 2, 4, -6. I kept the pivot and the numbers below it. Second pivot, I have 7, 14. So I kept the pivot and the numbers below it. Okay, then I am out of pivots. Okay, I'm out of pivots, but I know that I need something here, and I should have all ones on the diagonal. Remember that L is an invertible matrix. Okay, so I know I'm going to need a 1 here if I don't have any pivots. So if you run out of pivots, you fill in the remaining spots with 1s. Okay, 0s elsewhere. So it's lower triangular, so above's got to be 0. Now we're going to scale it. Okay, it's not really row equivalent. We're not doing row operations here. We are scaling by the columns. Okay, so I divide that whole column by 2 because that's what's in the pivot position. I'm going to divide this second column by 7 again because that's what's in the pivot position. So I get 1, 2, -3, 0, 1, 2, and 0, 0, 1. And there is my matrix L. So here's L, here's U. I said those backwards. Here's U, here's L. Multiply them together and you get your 3 by 3 matrix A. Okay? Now we said that when we're doing matrix factorization, they don't always have to be square. So let's look at one where it's not square. Okay, so new page here for a not square matrix. Okay, so A now is not square, we said. It's going to be a 3 by 4 matrix. So I've got 2, 0, 5, 2 on the top row. Second row is going to be -6, 3, -13, and 3. And then my third row is going to be 4, 9, 16, and 17. Okay, so remember to, so let's recap here. So I'm going to find an L and a U. Okay, to find U, I just do row operations. So U we know is going to be 3 by 4. Okay, I know A has to be I know L has to be invertible. So L is going to be 3 by 3 because I know to multiply, the middle spots here have to line up, right? The columns of the first matrix have to add the same number of positions as the rows of the second matrix. So those 3's have to line up. And if L is going to be invertible, it has to be square. So I know I'm going to be 3 by 3 there. So whatever size U is, the L is going to have the same number of columns and rows as the original matrix has rows. Okay, that 3, because U is the same shape, same rows and columns as L. Okay, so let's do our row operations now on A. Remember, that's our first step, is always row operations. So I've got my 2 here. That's my first pivot. Let's circle it. I'm going below that with my pivot now. So 3 copies of row 1 will be added to row 2 and replace row 2. That's 3 times 2 will get me 6. 6 and -6. -2 copies of row 1 plus row 3 is going to replace row 3. So -4 and 4. Okay. All right, I shouldn't say equals. That's going to be row equivalent. Okay, I'm going to unchange first row, 2, 0, 5, 2. Second row now, I'm going to have 0 because 6 and -6 is 0. 0 and 3 is going to make 3. 3 times 5 is 15. 15 and -13 is a +2. And then the fourth row here, 3 times 2 is 6. 6 plus 3 is 9. Okay. Now we're going to go to, so here's my new pivot. It's going to be right there. Okay. I need to write down row 3 still, so that's my new pivot though. 2 is going to make 0 and 0. 4 and -4 is going to be 0. 0 and 9 is going to still be 9. -2 here goes with -5. -2 +5 makes -10. 10 and 16 is going to add up to 6. And then -2 times a +2 is -4. 17 minus 4 is 13. Okay, so I need to get zeros below my next pivot now. So I need -3 copies of row 2 plus row 3 replaces row 3. So I'm getting 9 here. 9 and negative 9 will make 0. So it's going to row reduce. I'm going to get 2, 0, 5, 2. Second row's unchanged, 0, 3, 2, 9. Third row now, negative 3 and 3, negative 0 and 0 makes 0. Negative 9 and positive 9 will make 0. Negative 3 times a negative 2 is a negative 6. 6 and negative 6 makes 0. Negative 3 times negative 9 is negative 27. Negative 27 plus 13 is a negative 14. Okay, so my new pivot, my next pivot is actually in the fourth column. Okay, and I've got to the last pivot. This vector is U. Okay, so for L, I take the pivot when I found it and the numbers below. So I've got 2, negative 6, 4. Pivot, which is 3, and the numbers below it makes 9. Pivot, negative 14, and then there's nothing below it. And we said L had to be 3 by 3, so we are in good shape here. Now I just need to scale. Row 1 gets divided by 2 because 2 is in the pivot position. Row 2 gets divided by 3 because 3 is in the pivot position. And row 3 gets divided by negative 14 because negative 14 is in the pivot position. I should say column 1, column 2, and column 3. So I divide by 2, I get 1, negative 3, and 2. I divide by 3, I get 0, 1, and 3. And I divide by negative 14, I get 0, 0, and 1. And there is my matrix L. Okay, so LU factorization depends on the row operations. The row operations are the critical step to finding those L's and U's when you don't know them. Okay, you still have your equations if you know L and U, or maybe you already found them, right? Remember that UX equals Y and LY equals B. Write those again here just in case. And LY equals B. Okay, we use those to help solve systems once I have that factorization. Okay, it's that next step there. Okay, now one more thing. I said I'd mention diagonalization a little bit. So there's a special kind of factorization we're going to look at later, which is I can factor a matrix into this PDP inverse, where D has a special form where I only have numbers on the diagonal. Okay, so this is a 3 by 3 example. It doesn't always have to be 3 by 3. It could be 4 by 4, 5 by 5. But D is square and diagonal. It only has numbers on that diagonal. It's both upper triangular and lower triangular. Okay, so that's a diagonal matrix. Now, diagonal matrices are nice because when you have a diagonal matrix, what that means is if I do D squared, okay, well, when I go to multiply, I'm going to do D times D, okay? So I'm going to call this A, B, and C for my points on the diagonal, just to give them names. And then I'm multiplying by an exact copy of that matrix, A, B, and C. Okay? So when I go row by row and column by column, I get A times A is A squared, 0 and 0. Next row, I get 0, 0, 0, and 0. Third column, 0, 0, and 0. Okay, in the second row, I'm only going to wind up multiplying B squared here. So the thing to notice is that when I multiply a diagonal matrix by itself, I just wind up squaring those diagonal entries. Okay, so if I have all ones there, the identity squared is just the identity. 1 squared, 1 squared, and 1 squared. Maybe I have all 2s. Okay, well then I'm going to get 2 squared is 4. B squared, 2 squared is 4. I'd get 4, 4, 4. Maybe the entries go 1, 2, 3. Well, when I square them, I'll get 1, 4, and 9 because those are the squares of those diagonal entries. So that's another factorization, and we're going to talk about how to find that factorization in a later chapter, in chapter 5. Okay, but we kind of introduced the idea that there are other factorizations out there. So the other one we're going to deal with before the end of the semester is a QR factorization. Okay, so that gives you an idea of matrix factorization. Again, it's one of those things that it's not that it's easier, but it makes some other computations easier. It's another tool in our toolbox that we can use to facilitate our work, okay? Now, our next section is going to be 2.8. So we skip from 2.5 to 2.8. We do not talk about 2.6 and 2.7, okay? So we skip over those. 2.8 deals with subspaces. Okay, so we've talked about a space. A space is like Rn, you know, it's where all our vectors are kept. So a subspace is a particular piece of a space, okay? Hence the name subspace, okay? And we'll talk about a couple of special subspaces called the column space and the null space. We'll use those same linear systems and information we've been using to this point to solve problems and learn things and deduce different things about linear equations and linear systems. Okay, so I'll see you for 2.8 in the next video. Please be in touch if I can be of any help in facilitating your studies or your homework or preparing for quizzes, tests. You know, those checks for understanding come up. Check that checklist, see where those are, see where those quizzes are on the checklist. Make sure you complete those. And again, please contact me if I can be of assistance. All right, talk to you in 2.8.